All right, let's get this quick done over with. I'll try to cover all the Calc 3 theorems as quickly as I can and as compressed as I can, or all the line integrals and surface integrals, because I know there's a lot. There's like 1, 2, 3, 4, 5, 6, 7, 8. There's 8 things, all these theorems, all these different things, and I'll show you some easy methods to recognize whether you're calculating circulation or flux and the like. So, first thing we're going to cover is a line integral for scalar functions. So this is going to be we're going to cover some line integrals. So this is just a single integral using your line integrals. And you're going to have some function that's parameterized, right? So we're going to have the parameterized function, x of y is parameterized, and we multiply it by some magnitude of the derivative of our parameterization of dt of our curve. So this is your scalar. Let's write this scalar line integral. And this is just for scalar functions of line integrals. Scalar functions for line integrals, yeah. Okay, now we're going to calculate the vector part. So we have two different ways you can calculate vector line integrals. Oops, what did I do? You can calculate circulation, circ. You can calculate flux. All right. So circulation is calculated like so. You have a vector field, and this vector field is again parameterized, and you multiply it by just the derivative of your parameterization. You dot product actually. You dot product the parameterized vector field and your vector field. And your derivative, oh my god, you dot product your parameterized vector field with the derivative of your parameterization. So this is how you calculate circulation. And usually when you are calculating circulation, you're going to be using some derivative rather than a normal vector. So if you see r, like if you see, maybe if this ends with dr, this will be a circulation calculation. How about for flux? Well, for flux, you're going to, again, parameterize. But this time, you're going to dot product with some normal vector. And your normal vector is pretty easy to find. Your normal vector is just the x, it's just the parameterization, derivative of the parameterization of the y value with the negative derivative of the parameterization of the x value. And with a little more clarity, this right here is your derivative for your parameterization. And all you got to do is swap the places of the x and y values and then set negative on the x value. And you get your normal vector to dot product with your vector field. So these won't be important. The scalar line integral won't be important because now we're going to be in vector calculus. So let's cover Green's theorem. So Green's theorem basically says that you can calculate the circulation of a line integral only if the vector field is closed. So this has to be some closed region, and hence the circle on the line integral. So you have some closed region, and you can calculate the circulation using Green's theorem like so. So you find the double integral. So you turn a single integral into a double integral of some region, and all you do is find your q of x partial and the p of y partial dA. And this calculates circulation in Green's theorem. So let's write Green's. Let's write Green's theorem. And p of x plus q of y is to calculate flux d of a. If I want to be just a little more specific with this, this is the curl of your vector field right here for Green's theorem, and this is your divergence to calculate the flux. So if you find the curl of your vector field, you get this. And just a little more specificity, your vector field is defined by its first component as p and its second component as q, if you've never seen notation like that, or if you see m or n or anything like that. And another thing related to line integrals is that you can solve for a line integral using some potential. So potential function, and let's see, you can have a line integral of your potential function. So let's just write down, this is another way to write down that you're solving for circulation of your potential function. And you can solve it with some psi value of your bounds b. Let's actually write down a and b on the integral bounds. So you have a and b minus your potential function of a. And this potential function has certain requirements. The potential function must be the, I guess, the inverse gradient, or the vector field. Let's say it like this. The vector field has to be the gradient of psi. Which means that if you solve for the curl of your vector field, it will equal the zero identity vector. So if you solve for the curl of your vector field and it's equal to zero, the zero identity vector, then you have some potential function. And I have a video that teaches you how to solve for that. That's it for line integrals. We're going to move on to surface integrals. Now for scalar, so scalar surface integrals, your formula looks like this. So you have a double integral bounded by your surface of your parameterized scalar function. The parameterization is marked by two variables now, u and v. And u and v is just multiplied by the magnitude of the cross product of both partials. And this just gives you some normal vector of d ds. Or you can write this as du and dv. Now let's go just a little bit more depth in this. If you have some explicitly defined function as your surface, so z, not x, z is defined by some function of x and y, you can write your surface integral like so. So you can write it with, again, your parameterized scalar function with the multiplication of your u partial squared plus r of v partial squared plus 1 du dv. So only if you meet this condition of a explicitly defined function, you can use this form right here. And if you were to just work everything out, for an explicitly defined function, you're going to get some format that looks like this as well when you find your cross product's magnitude. So what's next? We have a vector. So we have to solve for a vector surface integral. So write down vector here. And usually first thing I learned was how to solve for the flux of your vector surface integral. And the flux is solved like so. So we have some surface with your vector field that's parameterized by u and v. And this parameterization is dotted. This parameterized vector field is dotted with a normal vector. But instead of the magnitude this time, it is just a cross product. So you get some vector back. dv. And there's a way if you have an explicitly defined surface as well in order to solve for this. So again, explicitly defined surface can be written as so. It can be written as the integral of the surface, double integral of your surface, with again parameterized vector field u and v times the negative of the u partial as the first component of the negative of the v partial of the second component of your parameterization, and 1 ds or du and dv. So this right here is if you have, again, a explicitly defined surface. I'll just mark it in red. Okay, how about for circulation? Well, for circulation, you need to use either some boundary, so you calculate the circulation over boundary, or you can use Stokes' theorem. So Stokes theorem. And cross products usually mean a normal vector, so I'll write down n over here for you guys. So Stokes' theorem, let's write down Stokes' theorem. Instead of circulation, let's write down Stokes' theorem. And Stokes' theorem is an equality. So we have Stokes's. And this is basically states that you can relate the circulation of some closed curve. So the circulation of some closed curve dotted with r prime of t dt is equal to the double integral of your curl of some normal vector. And this normal vector is dotted with, so when you do a curl you get a vector back, and when you do a cross product you get a vector back. So you're dotting your parameterized cross product partials, so this is a normal vector, with and du dv. This is Stokes' theorem right here. You have some circulation along a curve, and it's a closed curve, but you can also find the circulation using a surface integral. So the flux of the curl gives you a circulation for your vector field. So the flux of a curl. So what does that mean? Well, the flux is when you dot something with a normal. So you dot the normal vector with your curl, and you get some flux of a curl. And another thing, we have divergence. Maybe I shouldn't write this separately, but divergence. So we can rewrite this flux for the vector field here. So we can rewrite this. Rewrite with your parameterized vector field, dotted with some normal vector defined by this. I don't want to write down the entire thing, I'm not gonna lie. ds of ds of your surface. And you could turn this into a triple integral if you have a closed volume. A closed volume. And you can make it so that all you have to do is dot del with your vector field, and then you can find the flux. So this solves for flux. And let's underline this. This right here is just a rewrite of this guy right up here. So in conclusion, when you have some dot product with a derivative of your parameterization, it's circulation. And this is what Stokes solves for. Stokes solves for some circulation. And you can solve for the circulation by dotting, by finding the flux of your curl of your region. And the scalar surface integral can be written like so. This is only if these red parts are only if you have explicitly defined functions or explicitly defined surfaces marked by z. And divergence theorem solves for flux by turning it into a triple integral only if you have a closed volume. But this flux format right here, underlined in blue, is the general way that you can solve for the flux of a surface integral.